Okay, thank you, Nick. It is truly a privilege for me to be a part of a team, a much larger team of a bunch of super smart and super competent people, and I'm just happy to be able to share with you today some of the things that we're doing surrounding a tool called HAMR. So what is HAMR? Well, I usually describe it as a tool chain for building high assurance embedded systems, and we emphasize 3 different layers of development. So there's modeling, analysis, and verification, and standardized modeling languages, including SysMLv2 and AADL. And then there's component development, so working at the code level with C, Rust with Virus verification tool. And then we prototyped a lot of this work using Slang, which is a safety-critical subset of Scala with a contract-based verification framework which can be transpiled to C and Rust. And then HAMR supports deployment on multiple platforms, including the JVM Linux and the seL4 using CAmkES and Microkit. So if you're an seL4 adjacent person, why is this potentially interesting for you? Well, the seL4 ecosystem already has these tools like CAmkES and Microkit for helping you specify seL4 capabilities and kernel partitioning. So what we're trying to do is to add on top of that a layer for system engineering based on these standardized modeling languages. So the idea is that you can use these standardized modeling languages and tools that industry developers are already familiar with and using, like VS Code and then eventually Cameo for us. You can use that to configure the kernel, but then also do a bunch of other stuff. And that includes broader software, hardware, middleware modeling, adding architectural constraints and patterns. We have a number of sort of formal methods-oriented things in these modeling languages that we've added, like component contracts and model-level verification. And then there's support for assurance case construction and other things related to certification. There's also emerging support for other types of analyses that you typically want to do when you're working with seL4 and embedded systems. Then more broadly, what you get, especially if you're trying to communicate and work with and transition these tools into industry, you get connections with the broader industrial workflows for systems engineering. So including things like requirements engineering, being able to do some informal sketches of system development, and then also being able to connect with various sorts of domain mappings that people have already developed into these standardized modeling languages. So HAMR will take these artifacts, primarily the architectural models in this case, and it will generate not only the Microkit or CAmkES configurations, but also a bunch of other stuff that would typically help in seL4 development. So that includes auto-generating the Microkit code bindings, for example, the entry point skeletons, doing various things with helping you set up VM configurations, generating build scripts, and essentially what you get is a skeleton system that's immediately runnable, for example, on QEMU. You just do make and then run, and it's there and running. What also happens is because HAMR knows about these various formal method specifications living at the model level, it's also able to auto-generate various sorts of protection domain assurance assist, like unit testing infrastructure, code level contract information, and then again, it maintains this stuff related to certification throughout. So again, the high level goals for the seL4 community are to make seL4 more accessible, and then to some extent providing a framework for engineering verified applications on top of the seL4 verified kernel. So this work is part of a broader project that's led by Collins Aerospace. It's part of the DARPA PROVERS project, and that project focuses on integrating pipelines of formal methods in defense industry development processes. So again, sort of gluing together or chaining together different formal methods techniques starting with the model level. The primary industry demonstration project is from the Collins product line area called Launched Effects. So these launched effects are essentially small expendable UAVs that are tube launched either from the ground or from the air. And our objective is to help re-engineer or improve, developing essentially an experimental version of that mission computer that can demonstrate increased security and modularity and also decrease costs for development and assurance. There's all kinds of systems that you can develop using seL4. And so let me give you the characteristics or some examples of the types of systems that HAMR tends to work best with, because we're in the context of trying to demonstrate things for particular product lines. So imagine that you have a situation like before where you've got some sort of mission computer for a UAV. The typical thing that we're doing is saying, okay, let's take that legacy software, let's use the modeling language to indicate that we want that to go into a VM, and that is then will be placed by HAMR in a partition in the kernel. Of course, even putting this legacy software in a partition doesn't mean that you've secured your system. You still have the pathways into that mission computer. And so there's also an emphasis on developing various sorts of components that guard the information flowing into that mission computer. So this could be various filters or things that are looking to screen out malicious messages or malformed messages that might bring the UAV mission computer down. So the mission computer itself is legacy and untrusted. So there's a possibility that it could have bad stuff going on in it, like some sort of Trojan that is leading the UAV through a collection of waypoints to move to an area that it's not supposed to go. And so one of the things you're also doing is developing various sorts of monitoring components that sort of monitor the overall behavior of the system. You can't monitor for everything, but you're essentially trying to see that the behavior and the data flowing around with the system stays in the appropriate boundaries. And the idea is that these components are developed using Rust running on the bare metal and verified with formal methods. So HAMR will take this sort of thing and it'll create a build, right, that gets deployed on seL4, and you get all the seL4 goodness. Right, for these high assurance systems, seL4 is guaranteeing no infiltration into those. For this legacy code, no exfiltration of sort of bad behaviors, fault containment, and then no eavesdropping on the communication between the components. So again, there's this program emphasis from the Provers program on verified Rust as the basis of setting up these high assurance components. So I want to point out that there are a number of other talks in the summit that are a part of this project. So Darren Kofer will be presenting sort of like the big picture, how this stuff works in the context of the Collins product lines. Robbie VanVossen will be describing how the tool chain that I'm describing today, for a simple example, how it was applied to a much more realistic example as part of the Collins open experimental platform. Then there are several talks that speak to the general goodness of seL4. So Gerwin, immediately after me, will be talking about the infrastructure that Proofcraft has developed to help automate new seL4 kernel proofs for new platforms. And then we have both Gernot and Junming, who will be talking about sort of verified infrastructure and also techniques, new tools for verifying infrastructure elements of these systems. So I want to especially point you to Robbie's talk, because I am going to be describing this using a small, simplistic, sort of classroom-oriented example, and Robbie has taken this and applied it to this much more realistic example that's open and available for everybody to look at. So the idea is, just as kind of we described on the previous slides, there's some mission computer here. Here in this open system, it's based on ArduPilot. And then there are these high assurance components that guard flows into that mission computer. There's these two firewall components, a receive and transmit firewall. And so what Robbie was able to do is to model this system using the modeling tools. And then there were natural language requirements for the firewalls that he was able to translate into formal contracts that live at this model level. Then HAMR was run, generated all of this infrastructure, the VMs, various sorts of things for gluing together the components, managing the threading, and so forth. But then for these high assurance components, Rust skeletons were generated from those, and then also behavior contracts that were specified up here for the firewall rules. Those are brought down and presented as various contracts, and then you also get automated property-based testing support for those. So he's going to tell how he was able to verify this firewall written in Rust using Virus, and then how he was able to apply these testing techniques. Now, there's a bunch of other goodness going on related to assurance case development and things like that I don't think are going to be covered in the talks, but we have the ability to sort of explain and give you demos of those, and Darren would be a good person to talk to for that. So not to steal Robbie's thunder in any way, but just with the building of the framework, DornaWorks was able to find a 10x reduction in development time versus building this system by hand for seL4 and applying these model-based development techniques. Okay, I have to say a little bit about the scoping, because you're all like super duper seL4 experts, and you've probably got your favorite seL4 features, and you may see me talking and you think, well, that won't work for my particular feature. That may be true, because the project, even though it's building out a number of technologies, seL4, it's expanding that, it's funding further development of Rust, it's funding this modeling stuff. The main aim of Provers is to demonstrate a pipeline of formal methods working top to bottom. And so the challenge is, when you're trying to get this pipeline working, we have to necessarily narrow the scope so that we can get everything working end to end. And that's because when you're getting this pipeline going, you have to essentially identify key abstractions at the model level and then have those carried through all of the different layers to support the different types of formal methods that you're doing across all the layers. So the semantics of these abstractions has to be maintained and traceable across the stages, and then the claims, contributions toward the assurance of each stage, you've got to accumulate that and manage that and organize that somehow. So this means that the scope of what we're doing is necessarily limited, but when we're trying to stack everything together, but what you're interested in may still be able to be used in the builds for these systems. They're not just supported directly by all of the formal methods that we're working with. So this pipeline, because it's so important to have everything coordinated, this is supported by a formal semantics in Isabelle Hall, and this provides sort of our guidelines for how we develop the framework. We're not using this currently to prove the code generation correct. We'd like to be able to do that eventually, but that's sort of a huge task. And so again, you should think of this as sort of a guidance document that we're using to establish sort of the soundness of the contract language and other aspects of the framework. And we're hoping in the context of the Provers project to eventually connect that with, for example, a Microkit-based formalization. Okay. Let me say a little bit about AADL. So AADL itself, there's a standard. It's like 250 pages, so I can't describe everything. I will give you some flavor of what it looks like as a modeling language. Basically, what it provides is components, ports, and connections. Well, that seems pretty straightforward. But what it also does is it divides these components and connections into different categories based on the role that they play in the embedded system architecture. So for example, you see some components representing threads. And in the AADL sort of presentation, threads are the unit of schedulability. You see other boxes representing processes. So in AADL land, this means protected address space. So you can see that one of the things that we're going to need to do is to figure out how to map these standardized AADL concepts down to seL4, down to Microkit or CAmkES notions. So for example, the protected address space maps rather naturally to a Microkit protection domain. You also have categories of communication. So you have data ports, which are just shared data communication. You have event ports, notifications, which are queued. And then you have event data ports and connections which carry messages with payloads. So again, imagine how you would map that down to Microkit or CAmkES. Everything that's flowing between these components are value-based data structures, and AADL provides a standardized sort of modeling approach for describing these value-based data structures. If you're familiar with something as old as GUMBO AADL, it would look something like that. So when you're working with AADL, you get these component and other element categories that have some implied semantics. But then when you're building this system, you're not just connecting these together, you're also sort of configuring their semantics by attaching various attributes. So the idea is, for example, for threads, you can indicate if a thread is periodic, sporadic, and then as you indicate those choices, then you get specific timing or scheduling constraints that also get added in. For the connections, in addition to just specifying the basic categories, then you can also specify buffer sizes, your notions or constraints related to latency, and so forth. And so HAMR takes all of this information, the topology as well as these associated attributes, and that's what it uses to determine the shape of the code that it generates. In other words, the nature of the Microkit interface as well as the skeleton code that it's going to place in the Microkit interface. And it has to do additional stuff to make sure that it's adhering to these AADL semantic notions. So, yeah. Okay. AADL was great as a research vehicle across a number of industry research programs, both in Europe and in the US. But it never really caught on as a modeling language that was widely used in industry, primarily because its lack of industrial tooling, and also because it was a bit rigid in what it did. It had these component categories and so forth, but it didn't allow you to speak to the modeling of the broader sort of fuzzy context, you know, use cases, you know, other sorts of informal behavior diagrams and things like that. And so there's been an emphasis now as we're trying to figure out how to transition this technology to look at the new version of SysML called SysMLv2. So it has a number of features that everybody liked about AADL. It has both a graphical view and a textual view that are automatically synced. Many AADL modeling elements have analogs in SysMLv2, and it aims to provide a stronger semantics compared to UML or SysMLv1. And for us, one of the most important things is it will have wide-ranging commercial tool support as well as open source implementations. And so essentially what happened is that everybody that was working on the AADL standard got together and said, look, instead of developing a new version of AADL, we should just shift these AADL concepts into SysMLv2, and then bringing some other elements from the real-time embedded system community. So there is a designated work group within the OMG that's responsible essentially for transitioning AADL concepts into the SysMLv2 world. These are the leaders here. And the strategy for doing that is to develop what we can think of as modeling libraries. It's kind of like stereotypes, but different and better, right? So modeling libraries of AADL concepts that you can then use in the context of actually SysML modeling, but indicating AADL concepts. And we're actively involved in this committee along with a couple of other representatives from Collins. And it's kind of interesting that we're the ones that are sort of the most hardcore about building tools and especially formal methods-oriented tools and then applying them. So this is one aspect of what the end result looks like for this. So to get all of this off the ground, we developed a VS Code SysMLv2 front end for HAMR based on the SysIDE VS Code plugin. So here what you can see is that you have SysML component interfaces. You're importing and applying these AADL library properties to indicate which of the SysML things correspond to what AADL things. What you can also see here is that we've put in a lot of work getting contract languages. This happens to be the Gumbo contract language into these modeling environments and the SysMLv2 language in particular. You can see verification results from model level contract checking popping up down here. And then what's nice is you get all of your other sort of development, code level and seL4 level stuff right here. So you get your Microkit system description, you get your component source code, and all of that is part of the same integrated environment. So let me now give you a walkthrough using a simple example that's based on an infant incubator. This is the example that we're using to communicate these concepts with the broader industry teams on this Provers project. It kind of does an end-to-end walkthrough through these artifacts. This infant incubator, of course, the key thing is to keep the temperature good for the baby in the incubator. And so a key element is a thermostat component here, and that's what I'm going to be kind of illustrating things with. So the thermostat is broken down into a control subsystem that's controlling the temperature, and a monitoring subsystem that's giving an alarm if the temperature gets out of range. And so what you see here is that then that gets broken down into three tasks or threads in the monitoring subsystem, and then 3 tasks in the control subsystem. So we were able to take informal sort of designs from this original isolate document, model these in AADL, and then again, this is what we're using to illustrate concepts. So just to give you a flavor of what things look like in AADL, you get these graphical views of the components that indicate the ports and their categories and so forth, and then you get this accompanying textual representation. So here you can see there's 4 input ports, and they're typed according to this data modeling language types. And then there's a single output port. So the idea here is you're getting in, for this particular task, it's really the heart of the control task. You're getting in the current temperature, and you're figuring out if you should turn the heater on or off. And you're getting some desired set points that give you the desired temperature range, then also a system mode. So this is the character of this. Okay, so if you have this in AADL, how would you represent this in SysMLv2? Well, the idea is that you use the SysMLv2 core language. It looks pretty similar. You can see I have a part, I have some ports declared, and I've even declared them as inner-outs. And then what you do is you take these concepts from SysMLv2, from the SysMLv2 library, and you attach them to those parts indicating their AADL natures, so to speak. So we're indicating that this is a thread component, that we have data ports and things like that, and then we further configured these AADL standard attributes, in this case related to is this a periodic thread, a sporadic thread, or so forth. The nice thing is, if you look at these side by side, it's pretty understandable how you get from one to the other. So this helps in our tech transition effort to just give a little cheat sheet to people that know AADL, saying this is how you represent things in SysMLv2. All right, so everything is going okay so far, but a big limitation of SysMLv2 is it doesn't have a nice extensibility mechanism like AADL had. AADL had what was called an annex mechanism that allowed you to define your own little sub-language that could be incorporated into the base modeling language. So people in the formal methods community used that a lot to include their favorite contract notations or other sorts of semantic properties, and we don't have that in SysML. So we had to come up with a way to represent these behavior contracts. So again, I'm going to show you some simple natural language requirements for this isolate, but again, Robbie is going to show you much more complicated requirements and much more extensive use of this modeling language in his talk. So here we have some simple control laws, for example, for this one particular thread that's controlling the temperature. So what does it feel like for the developer? Well, they define their component interface, and then accompanying that, they define a component contract that formalizes these natural language requirements. Here's kind of an example of what one of those looks like. You can see that we start off with some traceability to the requirements, and then we have things that would look familiar to people that have worked with contract languages. Under the assumption that the mode is normal and the temperature is below the target range, then we need to turn the heater on to warm up the isolate, things like that. Okay, so what HAMR will do is it will take these architectural models, this contract information, and it will do the following type of code generation. I'll explain how this gets instantiated for seL4 in a second. So basically, for each thread component, it will generate infrastructure that houses that thread and connects it with the broader underlying threading infrastructure, scheduling infrastructure of the platform. Then for each connection, it'll generate an appropriate communication pathway based on the selected category of connection that's presented here. It'll also generate various types of information associated with setting things up on the platform. And then, importantly for the developer, it'll generate skeletons essentially for their entry points that they fill in to actually code components, and then those get deployed and integrated as part of the build. Now, for seL4, this means that we're generating the Microkit system description. And as you might imagine, each partition is specified with a protection domain. Each communication channel is specified with a Microkit channel. And then we have to add extra code in the protection domain that surrounds the user code to get these AADL semantics. And I'll say a little bit more about that later on. We are assuming that these systems are statically scheduled. And how we're achieving that is some of the UNSW folks developed a branch of Microkit for us that uses the domain scheduler to achieve that. It's likely going forward as MCS gets further incorporated into this work that we'll move away from the domain scheduler, but just so you're aware, this is how things are working now. Okay. Remember I showed you this diagram about the scoping of the pipeline. If you want to use the end-to-end sort of top-to-bottom formal methods pipeline, the threads that you're working with for the verification have to follow certain stylistic patterns. So these patterns are based on well-known patterns used in analyzable real-time tasking. And the idea is that they follow an input compute output pattern. So the idea is that every time a thread is dispatched by the static scheduler, behind the scenes, the infrastructure will pull the items off of the, essentially the Microkit channels into the view of the application code and freeze it. The application code then runs, and it can do various gets to read the data. It puts data in output ports, and then when the task runs to completion, those get pushed out to the communication infrastructure here. So what this guarantees in general for AADL-related things is that there's no external interference with the application port state while this code executes. And this allows you to do something important, which is interpret this task behavior as a function from the input port states and the local variables, right, to output port states and updated local variables. And this provides the basis of establishing the contracts for these tasks. So basically, the contracts speak to these frozen input states, the frozen output port states, and then these local variables. So the contract becomes a relation on all of those, and that's how the behavior is specified. So like I said, if you have a component that doesn't follow this task, you can still use HAMR to specify its interface and build it. It's just that the contract language that we're working with won't fully support reasoning for that. You can still use the testing infrastructure, but again, to achieve the verification, it won't work completely. All right. So a little bit more about how the protection domain looks. So HAMR will generate a protection domain, and inside of it is currently looking like this. There's auto-generated C code that essentially implements the Microkit entry points and interfaces with the Microkit level. And then what you have are Rust bindings to that C, and this is unsafe Rust. Then what you have is where the user works. And this is essentially safe Rust that has a bunch of, let's say, more abstract and nicely organized APIs that accesses all of this stuff behind the scenes. This is the boundary at which you do the Virus Rust verification. To make all of this work, ghost variables are used to abstract what's happening behind the scenes in this infrastructure world so that you have a nice, clean view for the developer. These Virus contracts get auto-generated from the modeling contracts, and so the users, as they're typing, this is being constantly checked here. And then HAMR is also generating, for that particular protection domain, executable versions of those contracts that can be used both for runtime monitoring and for unit testing. And it's also supported by a property-based testing infrastructure that's sending randomized values into this user code in the protection domain and checking them against the contract. So the application code that the user is writing goes here. Okay, let me give you some examples of how this is working, and then we'll do a little demo. So again, if you have this component shape with a contract at the modeling level, what HAMR is going to be doing is generating what I just showed you on the previous slide. If you open that up in VS Code, this is what it looks like. You get here, I'm showing you a little fragment of the generated contract, and then this is the skeleton where the user is going to add their application logic for this component. In this little case, it's the little controller, so we'll be implementing the control laws in Rust for this heat control. As you're working, Virus is constantly checking. So when you start off, it's going to say, well, your contract is not satisfied, right? Because you haven't added anything yet. But the idea is, as you add your code, according to this contract, you can see that this is the auto-generated version of the model level contract that I showed earlier. Virus will be checking. So the typical thing that you're doing when you're programming is you're not working, again, directly with these sort of lower level Microkit APIs. You have for each port a dedicated getter and setter that's generated. So when the user works, you can say, oh, I'm going to get something from that port, or I'm going to put something to that port. You can see both of those being used here, and then Virus is constantly checking in the background, and if you've done everything correctly, it's going to say, oh, no problems have been detected in the workspace. So let's do a little demo and see what some of this looks like. First, starting with the code generation. So this is a prototype, so you might imagine it being done in a little bit slicker way eventually, but this is taking advantage of some of the built-in VS Code features. So what you see is the model, the SysMLv2 model in VS Code. A certain part of that model, let's say a certain subsystem, is what we're going to be used to generate code for, and the rest is sort of sketchy descriptions of the environment into which that system is going to be placed. And so the first thing that you do is you can run a configuration option, and you can choose the platform that you want to deploy on. So here you can see the different platforms that HAMR supports, and one of those is Microkit. There's also CAmkES stuff in here somewhere. So I must be, what am I, yeah. So you'll select that you want Microkit, and then it's going to ask you some simple options that you want where you're going to put the output. It provides that configuration in the model so you can use it over and over again, and then when you want to generate code, you just say run the code generation, and you see the code generation happening here, and it's generated the code successfully. It's important to understand that this is an iterative process, and so HAMR takes great care to not clobber existing code if you change the model and then rerun the code generator. I don't have time to explain that in the talk, but there's been great care put into that type of capability so that this can truly be an iterative experience for the developer. Okay, so now what we're going to do is open up this one particular task, this manage heat source task in the same IDE. We're going to open its application code. That is where we'll program in Rust. So we open that, and this is what it looks like. The contract information that was present in the model has been extracted and distributed in various ways. The ghost variable set up, the contract set up, this appears in the main entry point for this particular thread, for a periodic thread, the time-triggered method. I should say if these are sporadic components, it's more complicated, which is what I'm not showing. For sporadic components, you get dedicated event handlers with contracts for each coming input event port. So the important thing is this is sort of your objectives for what you're the behavior you're trying to meet as you're coding. You're going to put your application code here, and immediately, as soon as I start typing, Virus is working saying, well, you haven't satisfied your contract yet. So it's like, yes, I know, because I haven't done anything yet. But as you start typing, you're trying to remove these types of errors. So here we're going to see the developer adding application code to the skeleton. So it's magically complete. I've skipped all of the coding steps. And so now let's see what happens if we have an error. So I'm going to seed an error here. I'm going to tell the heater to turn off when it should turn on. Immediately, I mean, Virus is really fast. Immediately, it's checking to tell me, oh, there's an error in the contract, and you should fix that. So that's what's happening here. And if we go back, we fix that, Virus will tell us that everything is okay. So I don't have time to demo any of the testing stuff, but I'll give you a quick explanation of what that looks like. Basically what happens is that in addition to generating these Virus contracts, what HAMR will do is it will generate Rust Boolean functions that implement the semantics of the contract. And then it will combine those Boolean functions into precondition and postcondition functions that can be called as part of a testing oracle. Those get automatically, let's say, available in testing infrastructure for the developer. I can imagine a test case, I can write the inputs down, I can call this infrastructure, it immediately checks that test vector against the contract. But more interestingly, what HAMR will also do is generate randomizing generators for your input ports here that just shove repeatedly values through the component, testing it against those contracts. So there's also emerging support for checking the coverage information of that code, so you can tell if you need to tweak these generators to get greater coverage. And you should ask Robbie after his talk about his experience in using this framework. So there are some details here which I'm going to just skip, but this is what gets auto-generated from the developer. This is all they need to see. It's a Rust macro with your generators already pre-configured. You press this button and thousands of tests get generated and checked against the contract. If you want to modify these, again, to get better coverage, then there's easy ways to customize those. In this case, we're illustrating how these are customized to get by narrowing the ranges of the values in various ways. So I'm a big believer, and HAMR is designed around the principle that every single formal methods contract is also testable in some way. And the semantics should be completely aligned. And so this allows developers to easily move between testing, automated testing of the components, and verification. So you can sort of debug things, debug your contracts, and then move to full verification. Another nice thing is if Virus contract checking is failing, you can use the testing infrastructure to try to find a counterexample that you can immediately present to developers so that they can run through the debugger. Almost done. I want to say one more thing about this entire approach. If you're trying to align things like the semantics of testing and the semantics of verification, it's very important that you understand exactly when you write, for example, a formal looking predicate in the model, what exactly that is constraining in the seL4 execution. So you need some sort of framework that establishes the correspondence between every modeling element and every formal claim that's presented in the contract down into the code. And there's been a lot of effort in the tool to make sure that that happens. So there's a traceability reports. Traceability reports are generated to link all of these things up. And then moreover, what you want to ensure is that nobody goes in behind the scenes and modifies the model without rerunning or modifies the test stuff, right? So that it's misaligned with the model. And so there's a framework called attestation that's developed by the University of Kansas folks, which cryptographically signs the correspondence between all of these, making sure that they're aligned. So just to give you some idea about what happens with that. So if I have a port here on the model, part of this traceability information is, and this is from the GitHub READMEs that are generated. I can click on that, and it'll directly link to me in GitHub where that port is declared in the SysMLv2 model. Then I can click on this other hot link, and it's telling me directly where the API for that port is implemented in the Rust code. And then it's telling me exactly where that is in the Microkit system description. So again, all of this stuff is auto-generated, with a bunch of other stuff. If you want to know about the behavior constraints for each clause in the model level contracts, again, you can click on that, see those in the SysMLv2 model. You can click on the Virus link to see where that particular contract clause is in the Rust code. And then you can click on this also to see where the executable version of that contract lives. So again, it's maintaining this traceability from top to bottom. So, what are some themes that I would like to leave you with? The first is the general theme of raising the abstraction level. seL4 has been so great and so influential in terms of being able to have high assurance infrastructure. And so part of what we're trying to do is to raise the abstraction level, not only by including these modeling languages, but in some sense emphasizing the notion of perhaps picking out patterns for the different protection domains, and then having the developer's view of using seL4 organized around those protection domain patterns. When we're able to do that, we can pick patterns that are more amenable to component and system assurance, and we can figure out ways of representing those patterns in standardized modeling languages, so you don't have to look and work with the lower level details, even at the Microkit level. Another thing is, if you have these higher level abstractions, you can do more for auto-generating support for seL4 development, including things like I mentioned before, the build scripts, the VM configurations, various sorts of testing and logging. Another major theme is to try to have specifications that can be leveraged for both verification and testing. Finally, we want to make sure that we're working to integrate these concepts to make seL4 more accessible within these broader industrial workflows. There's a number of other things that we're working on in the short term. So one is system reasoning capabilities. So you noticed that I haven't said anything about composition of these components and how would that look and what can you verify there. So we're actively working on rolling out a framework for that, and it's again going to emphasize this notion of combining testing with formal verification. So the first capabilities that are going to be emerging are things related to testing and runtime monitoring. There's also a bunch of stuff that can be improved for efficiency reasons by bringing in additional sort of Microkit as well as goodness, as well as other things that are emerging from the seL4 members of the team. So I'll leave you with those thoughts. Okay. Sure.
Great talk. I'm curious about a bit of, my question is a bit with compositionality, which you call future work.
Right.
These contracts you're talking about, the boundaries they interact with, like the informal descriptions of requirements is one boundary that came up.
Right.
Another is sort of the fuzzy environment in which a model is expected to operate.
Correct.
Is there a good story for relating like those informal descriptions to the actual contracts, or the environment to the contracts that were used internally in a system that can show up as constraints on the environment, or should be related to contracts for the environment, that kind of thing? It seems like it's tied to your compositionality work.
Yeah, very much so. So part of the issue is that the program itself really isn't tasked with working on that particular issue, but it's certainly important. And I'm a big believer in providing various tools to, to animate these contracts to help developers essentially validate them against what they're expecting, in the informal world. So that is something that is, very near and dear to my heart. The tool chain isn't directly supporting that at the moment. Again, one of the things that we're always trying to do, though, is to be able to illustrate behaviors related to the formal contracts via actual executions derived from testing and simulation. So that's the best that we're currently doing in the short term. Yeah. Yep.
I see that you are extracting information from the SysMLv2 model. I'm wondering how you're doing it and how satisfied you are with the mechanisms of accessing the model data.
So what we did is something very straightforward. We have this open source plugin for VS Code, SysIDE, which was developed by another group, which I very much appreciate. So we're using that open source tool, and we're essentially walking over the abstract syntax trees of that model and translating it into an intermediate language. Now, there are emerging facilities within SysMLv2 that essentially take your in-memory representations of your model elements and represent those in a database. Longer term, it's a standardized database that you can query and diff and all of this stuff. So longer term, that's probably what we're going to do. To get the contract information into the model, we had to do some extra tricks. So the contract information is represented using the SysMLv2 language construct, which is essentially a comment. And so we had to build a lot of tools for parsing out that comment, doing syntax highlighting, and doing name resolution of that comment against the regular SysMLv2 modeling elements. Yep.
That sounds excellent. I'd be worried with the API that the SysMLv2 working group proposes at the moment. I think there's some troubles with it. But on another note, I understand you have Rust bindings with unsafe. Do you have any mechanism or what method do you use to assure that this unsafe does not introduce any undefined behavior?
Yeah. So right. Yeah. So that diagram that I showed with sort of the brown stuff and all of that, indeed, that is not verified. It's stuff that the user doesn't have to touch. And so, in essence, what you're doing is trusting that the tool did the right thing in that case. We would eventually like, for example, to extend the Rust boundary out and replace the C altogether, have the Rust binding directly to Microkit. But this is a way that we could get things going and also use the same sort of gray stuff that we're doing here. The same code is used there for the C components that are generated as for the Rust. But you're correct in the sense that all of this is unverified and trusted. What you're doing is you're trusting that the tool did the right thing to set all of this up. Eventually, we hope to prove this correct using some techniques that we have in mind.
Is it possible to run it in memory or not?
In what? I don't know anything about that.
Thank you.
Yep.
Are there any quick questions? We have about a minute left.
Yeah.
Kind of low level, you mentioned that all the gets sort of happen before you do the computation, and then all the puts happen, sort of the model for how you handle most of the verification that you're doing. Are there publicity problems with like the gets, or is that just handled somehow separately?
So there's no problems in implementing it. What you're doing, or what the code is doing now, though, is actually copying in the contents into essentially the user area for the user to work with. So the original motivation of doing that in AADL was to get a coherent, single snapshot at one point in time of all of the inputs that were then frozen as the code executes. Yeah. But there are efficiency issues with that. And in fact, you don't necessarily need to make these copies if you're controlling potential interference with the scheduling or other aspects. right? And so one of the things that we're doing is looking at ways that the various other sorts of goodness and the device driver, I always get the acronym wrong, SDDF, you know, these things can be used to optimize these in some cases because, for example, in some of our applications, messages are just being passed through, right? They're not being modified at all. So the point is that this abstraction is provided to the user and the contracts are set up to support that abstraction, but in the actual implementation, a variety of optimizations are possible. Right.
Is there any assumption in the contract that those three things came like at the same instant?
Yes.
Even if they're not, because you're getting one, then you're getting two.
Okay, so what happens is behind the scenes there's a service called receive input that makes all of the state available at once. But then the user accesses that saved state through the gets. So even though the gets are distributed in the code, they're referencing this saved snapshot that was created by the underlying service called receive input. Yeah, okay.